Okay, so now we're going to talk about the gem5 standard library. So Matt talked about how we have the models, which are in C++, and then the standard library is wrapping those models with particular parameters set, and then we have the simulation environment. So the standard library is really about all of the having components that are specialized models, and then controlling the simulation. So that's what we'll be talking about in this section. I'll also note that the standard library is something that is relatively new. I think we started working on this a few years ago. So we are trying to expose all of gem5's features in the standard library, but this has not quite happened yet. Okay, so I'm going to talk about some concepts of the standard library. Then I'm going to talk about using the components module. Then I'm going to talk about using the simulator module. And then we'll go through some examples of how to make gem5 faster using fast forwarding and checkpointing, and then end with how to do use the pre-built resources, which we are getting more and more good resources out there for you. Okay. So as we've seen, we have this configuration file or the run script that we feed into gem5. It's incredibly flexible. But if you're not using the standard library, it requires hundreds, if not thousands, of lines of Python code to configure a complicated system. Say you want to do full system x86, you have to declare all of your cores, all of your caches, all of your devices, and lots of other stuff, and you end up with thousands of lines of code just to get the simplest full system example going. But as we saw a minute ago, with the standard library, it's only like 4 lines of Python code. So the standard library kind of sits in between all of these models that are in C++ and running things in gem5. So the idea is that you can quickly create systems and start running things. And we especially want to give you reasonable baselines. Again, this is a work in progress, but that's the idea. The idea is that we're going to be taking these components and be able to like plug and play them, like Lego style with these components and quickly swap them in and out. So the main idea behind the standard library is this idea of a board. So you can kind of think of this like the motherboard of a computer. And you can kind of think of the standard library components as if you go to a Micro Center or something and start buying components for your computer, you need to buy a board, you need to buy memory, you need to buy a processor, and then you plug them all together. So the standard library components are the same kind of idea. We have a board, you can get a processor, plug that processor into the board, you can get some memory, plug that into the board, and then the other thing that we have in gem5 is the cache hierarchy, which you can also plug into the board. Obviously, real systems, the cache hierarchy and the processor tied closely together, but in gem5, we often want to be changing the cache hierarchy. Okay, so with that in mind, let's go to our second example and build a board with our own versions of cache hierarchies and processors. But before I do that, are there any questions on this conceptual view of the standard library?
Any questions? Yeah, go ahead. Yeah.
Are each of these a sim object? The board's a sim object too?
Kinda. How do I answer this in a way that's not terribly confusing? The board, a lot of the stuff in the standard library is in pure Python. And it's really just there to hook together all of the C++ modules. I could go a lot deeper, but I think that's kind of the level that you're asking the question. Does that make sense?
So my understanding from before was that the sim object includes the C++ file and the Python, I guess, interface to that C++ file. And
Right.
you're saying this is like another Python interface on top of that wraps it all together.
Yeah, exactly. That's correct.
That's how I think.
The standard library is another level of interface. Yeah, exactly. So you won't find processors, cache hierarchies, and memories. You won't find a C++ version of these. These are pure Python, and they are wrapping the C++ modules, which is definitely a bit of a confusion, but we'll see more when we extend the standard library in a bit.
Sorry, I didn't mean to interrupt. Any other questions? Okay, go ahead, Jason.
Okay, cool. So let's go to this file. So so here we are with all these imports. I will say that Bobby Bruce, who did a lot of the development of the standard library, clearly comes from a Java background, and that he loves to have lots and lots of imports. Not the way I would have designed it, but that's the way it's designed right now. Okay, so what we're going to do is first create a main memory. So as main memory, we're going to use this single channel DDR4 component. And then we can optionally set a size. If you don't set a size, it'll default to what a single channel DDR4 DIMM size is, which I think is 8 gigabytes. But I would strongly encourage you to set a size of, say, 2 gigabytes, because things will run a little bit faster if you do. So we're going to create a main memory. Now we're going to create some caches for our system. In this case, we are going to do a private L1 shared L2 cache hierarchy. And this is from, so this is from the classic caches, and we'll talk about the difference between classic and Ruby and Chai in a moment. But this is a private L1 shared L2 cache hierarchy. And you should be able to see this help, which kind of tells you all the different parameters you have to set. So each cache, the L1I and D, as well as the L2, you need to set the size and the associativity. So let's do that with some reasonable values. So L1D associativity, let's do 8. L1D size, let's do 32 kilobytes. L1I associativity, we'll also do 8. L1I size, let's also do 32 kilobytes. L2 associativity, we'll make it 16 so that we don't have too many invalidates from the L2 to the L1s, and the L2 size, megabyte. You can choose whatever values you would like for this. All right, any questions so far? Okay. So now let's create a processor. So let's create a simple in-order processor, which we're going to use this simple processor class to do this. So in the simple processor, this is not something you would necessarily want to use for research, but it's something that's good to kind of get started with this. So we're going to use the CPU type of timing CPU, as opposed to not a timing CPU. We're going to use 1 core, and we are going to be using the x86 ISA. Gem5 also has good support for RISC-V and ARM, but since we're using an x86 system, it's usually easier to get started with the x86 ISA. Okay, so we have a main memory, we have caches, and we have a processor. That's good. All right, hopefully everybody has gotten up to this point. I'll jump through the slides real fast. So we did a main memory, we did caches, and a simple in-order CPU. So a quick note here on the simple processor. This is not meant to model any real processor. It's a simple thing to get you started, and don't use it for research if you care at all about CPU performance. Okay, so now let's plug all these things into the board. So now I'm going to jump back over here. So we're going to create a board. This board, we're going to be using our simple board. So the simple board is actually flexible enough to use any ISA, but I don't think it can do full system simulation. It can only do syscall emulation. And we'll talk about that, what that is in a minute. So let's plug our processor in, which is our simple in order. plug our memory in, which we called main memory, and plug in our cache hierarchy, which we called caches, and finally set a clock frequency. So let's run this at 3 gigahertz for fun. Okay, so now that we have our board, we now can set a workload on this board. Again, we're going to obtain a resource from gem5 resources. This time, let's do something a little bit interesting. So we have some benchmarks up there. So in this case, we are going to be using x86, NPV. So NPV is the Nash parallel benchmarks. IS is a simple benchmark that does sorting. We're going to do the smallest size, which is size S. And then we're going to do the workload version of this. So this is going to download things for us, set up all the parameters in the background. We don't have to worry about it. And then this allows us to then create our simulator. With our board. And then we can do simulator dot run. So I know I was going through that kind of fast, so I'll leave this up on the screen for a minute. And then in this case, we can use any of the gem5 binaries to run it. So we'll just use the bare gem5, but you could also use gem5 messy. And we are going to run 02 components.py. Okay. Before I run this, any questions? I'm going to assume that there are no questions, or I'm talking to an empty room. It's hard to know. Okay, so let's run this. So this will take about 30 seconds to run. So this is taking this binary for IS and executing it on the simulator. So the simulator is executing instruction by instruction with this simple memory going through the cache hierarchy, or sorry, the simple processor going through the cache hierarchy to our DDR4 memory. So that's why it kind of takes a little bit. While that's running, let me pop back over to the slides. So we set our workload, and now we can run this example. My paths here are not correct. Apologies for that. Okay, so it takes about 40 seconds. And then we'll look at the output of this. Okay, so now it's done. So you should see that it printed some size, the number of iterations, and then the amount of time that it took. So if we look at the stats.txt, you can see that it took less than 2 milliseconds and executed, it looks like 31 million instructions to complete this. And then there's lots of other stats as well. For instance, if you're interested in the IPC was 0.5 for this workload. How are things going over there? Matt, any questions?
Any questions? Looks good.
Okay, great. Okay, so that's our first example, actually using our own components in the standard library. So I want to talk a little bit about the components that we give that are available in the standard library. So if you look at, so the standard library is defined in the gem5 module. So in this, we have components and pre-built boards. So 2 different kinds of components. These pre-built boards are boards with all the parameters already set for you. For the most part, they're not going to have any options to send to it. And the components are components that you can use to build your own boards. So we have 2 different pre-built boards right now, though we should be having more very soon. I was actually supposed to give an Oscar talk at ISCA today as well, which I can't be there for, about another pre-built board that we should be pushing very soon. So the demo board is just a demo, as we saw. The RISC-V matched board is a somewhat accurate model of the Sci5 unmatched RISC-V development board. And then we also have boards, cache hierarchies, memories, and processors, as we talked. So if we look on the boards are the things that we can plug into. The simple board is an SE-only board, and we'll talk about syscall emulation in a minute, and it's relatively configurable. And then we have an ARM board, a RISC-V, and x86 board, which are ready to be extended for full system simulation for those ISAs. Under cache hierarchies, we have 3 different types of cache hierarchies. The Chai cache hierarchies, classic cache hierarchies, and Ruby's classic. These have a fixed, so the idea of a cache hierarchy is that it has a fixed interface between the processor and memory, and the cache hierarchy sits in between. So you should be able to plug in any cache hierarchy with any processor and any memory. Ruby has some detailed cache coherence protocols and detailed interconnect. The CHI or Chai, I'm not really sure how you say it, to be honest, is based on the ARM protocol, and it's a specific ARM protocol that's been implemented in Ruby. And then the classic caches are relatively flexible. You can kind of create any hierarchy you want, except that you're stuck to this hierarchy of crossbars, and you don't have any control over what the coherence protocol is. It's just kind of baked in. For the most part, I personally will sometimes use classic caches if I'm just prototyping something, but then when I really care about the performance of the system, I switch over and use a specific Ruby protocol or the CHI protocol. I think I just said all this, so oh yeah, so quick caveat here. When you're choosing different cache hierarchies, you actually need different gem5 binaries. If you're using classic, you can use any gem5 binary, but if you're using Ruby or CHI, then you have to use that particular binary. So in the development environment that we have in the code spaces, I have 3 different gem5 binaries for you. gem5, which is using Chai. gem5 Messy, which we've already used, which uses a Messy 2-level protocol in Ruby. And then there's another one, gem5 Vega, which is going to be used this afternoon as we're doing the GPU stuff, which uses the GPU Viper protocol. Okay, so that's about cache hierarchies. We also have a bunch of memory components. So these are pre-configured, both LP DDR and DDR 3, 4, and 5 DIMMs with single channel and multi-channel setups. There's also integration with other DRAM models like DRAM Sim and DRAM Sys. But I want to emphasize that you don't need to use DRAM Sim or DRAM Sys to get a highly accurate DRAM simulation. gem5's DRAM model for DDR controllers, HBM, and LPDDR is highly accurate and within a couple of % of these other systems. And then we also have HBM, which can give you like a stack of HBM to integrate it into your system. Okay, and finally, we have processors. Right now, we have 3 different processors. I expect to have more processors that are tailored to particular pieces of hardware coming soon. So most of these are configurable things, which I try to shy away from, but that's where we are right now. So 3 different types. We have the generators, and this is generating synthetic traffic, but they can act like a processor in your system. So you can test your cache hierarchy or test your memory using these generators. We also have simple processors, which have a bunch of default parameters, specify one ISA, but are not particularly easy to specialize. So we'll kind of see how to specialize a processor in a minute. And then we have a switchable processor, which we'll see more on it later, but allows us to switch between different processor models dynamically while we're simulating. So one other statement on processors. So a processor is made up of a bunch of cores. Each one of these cores has a base CPU, which is the actual C++ model. And then the processor in the standard library is kind of what allows you to interface between those cores and the cache hierarchy and the board when we're doing full system simulation. Okay, I know that's what was a lot and kind of fast. But any questions on these? I guess I have a couple more things to say about processors, but I'll pause here for a minute and see if there's any questions on what I've been saying.
Any questions about processors in the room? Good.
I guess. I don't quite understand why there are three binaries, no gem5, gem5 ISCA, and gem5 Vega. Seems a bit confusing. Why is there just one binary, like three backends? Is it like a design decision, again, is it something?
Yeah, so it's legacy. I would much prefer having one binary. But it's to fix that is a lot of work. This really stems from the fact that, you know, Matt talked in the beginning how gem5 is a combination of Ruby gems from Wisconsin and M5 from Michigan. And this is part of this legacy code, right? So these code bases have been around for over 20 years. They were started around the turn of the millennium, around 2000. And so we just have a lot of this legacy stuff that we carry along with us. And having multiple binaries for cache hierarchies is one of these legacy annoyances.
Yeah, it was just a question, it was like a decision, or it was like, okay, it's a big effort to move everything, yeah, that's a good, but thank you.
Yeah, it was not a design decision. It was just, that's the way the code was when I started working on it 15 years ago. And it's still like that.
Just to add to that, Jason's being a little modest here because he has started work on, this is something that play about search project where it was sort of contributing their free time. So, and yes, one more question.
Yeah, that's a good question though.
In terms of accuracy, these three kind of processors are equally accurate. For example, for benchmarking. Sorry, my.
Yeah, that's a good question. So we have some different kinds of processor models, which is what I was about to talk about. So thank you for that transition. So we have, depending on how you look at it, 3 or 4 or 5 different processor models. So we have the O3 CPU, which models an out of order CPU that has, you know, a reorder buffer, branch predictor, physical register file, etc. This is highly configurable, but I'll be honest with you, even if it's configured correctly, it's not particularly accurate for modern out of order cores. It was based on this code was written in the mid 2000s, so almost 20 years ago. And so this is some top of my priority of things to improve in Gem5 is the out of order CPU. We have an in order CPU that we call minor CPU. This has a 4-stage pipeline. The pipeline latencies are all configurable. It has a branch predictor, everything you would expect with an in order CPU. It's highly configurable as well. And if you set all the parameters correctly, it can be similar. You can get quite similar performance to modern high performance in order designs. So for instance, the RISC-V matched board has a very specific configuration that models the Sci5 processor that is in that, the RISC-V unmatched development board. Then we have the simple CPUs, which there are 2 different types of simple CPUs. The timing simple CPU, in this case, every instruction takes 0 cycles. It just takes however long it takes to fetch the instruction from the iCache, except memory instructions, which take whatever latency goes to memory. And then we have the atomic simple CPU as well, which can be used for fast forwarding. We'll talk about that a little bit more later. And then the other CPU model we have is what we call the KVM CPU. And I'll also talk about more about that later. Mostly for timing, you'll want to be using the O3 CPU for out of order and the minor CPU for in order. And the simple CPU can be useful if you don't care that much about the CPU timing, but just want to drive memory accesses. Does that answer your question? Great. Yeah, so this is a little bit more. So those are highly configurable. You can see these base O3 CPU and base minor CPU files if you want to see how to configure it. You can also on these processors or core models, every single instruction can have a different functional unit, or you can have a functional unit that executes multiple instructions, and you can specify the latency and the pipelinedness of each of these functional units, and lots of other options as well. Okay, any other questions about boards, cache hierarchies, memories, processors, standard library, components in general?
Any questions? It looks like no. Go to an example.
Okay, cool. So the standard library components, were designed here around extension and encapsulation, specifically not designed for parameterization. We try to use object-oriented design and good software engineering practices so we don't end up with these like massive unreadable configuration files that we're feeding into things. So if you want to create a processor or a cache hierarchy or some kind of new memory with some other parameters than what we've provided you, what you should do is extend the things that are already there. So let's see an example of how to do this. So a quick reminder, we have these models in C++, and then the standard library in Python. So what we're going to do is create a new component, a new processor, which takes one of the cores, specifically the base 03 CPU, and specifies its parameters. Okay, so that's our goal, is to create a new processor with some specific parameters on an 03 CPU. All right, so we're going to be using the 03 processor.py file. This is mostly the same as what we saw in our last example, but now we've added this line that has my out of order processor instead of my simple in order. And we want to have a width of 8, a ROB size of 192, and then integer register files and floating point register files with 256 physical registers. So let's pop over and see what we need to do to complete this example. Okay, so what we are going to do is fill in these two classes as we go. So if we scroll down real fast and look at this code, this looks very familiar. Basically what we had before, we're going to use the same workload. Same cache hierarchy, which I guess I did. I'll change this to 1 megabyte since that's what I used last time. And then we have this out of order processor with these options. So let's start with the core that we are configuring. Okay, so we are going to extend the base CPU core, which allows us to just specify what core model we want to use from gem5, and then we can specialize it. So we need to call the superclasses constructor with underscore init, and then pass into this a core that we want to use. So in this case, we're going to use the x86 03 CPU. And then we're going to set this to the, use the x86 ISA. It's a little bit repetitive, but there are reasons that we have to do it this way. Okay, so after the base CPU core initializes the C++ model for us, we want to override some of these parameters. So we want to be able to set the width, the ROB size, etc. So if we look at the base CPU core, so if you look at base CPU, base 03 CPU, in code spaces or in Visual Studio Code, you can do Control P and type the name of the file you're looking for. If we look at this file, you can see all of the different, so this is our base 03 CPU. These are all the different parameters we can set on it, which are a lot of parameters. Most of them have defaults, which you may or may not be able to trust. So we're going to set some of these parameters. So we're going to do self.core, which is the actual sim object that we're working with. And we're going to set all the widths to be the width. So we're going to set the fetch width to be width. again, if you don't want to type along with me, in the completed directory, you can find all of this written already. So fetch width, decode width, rename width, issue width, write back width. So as you can see, there's lots of parameters here that need to be set. I missed. That. Okay, so we set all the widths. Self.core.num rob entries for our rob size is in regs. So our physical integer registers is going to be num int regs core.num is float regs p regs. Let's set the branch predictor to the tournament predictor. Probably not the best branch predictor, but it's something that we can use. And finally, let's go ahead and specialize the load queue entries and the store queue entries. All right. Again, if you don't want to type all that along with me, you can find this in the completed directory. So small chance that I actually typed all that correctly as we were going. Okay, so now that we have all these parameters set in my out of order core, which I will make this a little bit bigger. So we need, in the processor, we're going to instantiate some of these cores. So we're going to say cores of the processor. So cores needs to be a list, but we're just going to create one core. So we're going to do my out of order core with the width, rob size, num int regs, num fp regs. You're just going to pass these parameters through. And then once we've created this core, the base CPU processor allows us to create a processor using base CPU cores. So we're going to pass those cores in. So what I really want to try to get across, other than just typing a bunch of stuff out, is that, you know, if you want to specialize this O3 CPU, the way that I would encourage you to do it is by using this object-oriented design and creating your own core and your own processor with this. So now that we've done this, we should be good to go. So let's see if this works or not. So we're going to do O3 processor, and I'm actually going to set a different output directory. So instead of using m5 out, I'm going to create a new directory, which is m5 out /000. So I can kind of compare the output from the O3 CPU to the output from the simple in order that we saw a minute ago. Okay, so run this. Amazingly, it looks like I didn't do any typos. So this is going to run. And what did I say? This takes about 2 to 3 minutes to run the script. So while this is running, I'd be happy to take any questions. I think I can pop over here and show you this code as well.
Okay, I don't see any questions, Jason, so I guess we'll just wait for the run to complete.
Okay, so yeah, we created these two subclasses and now we're running. So one of the questions we might want to ask is this faster than that simple in order that we did? So I saved this output to a different directory, as I kind of showed you. So passing ---- out or to gem5, so it would save in a different place. And we're going to compare these two stats.txt. So while this is still running, I'll go ahead and open up the stats.txt from, so this is the simple in order. Oh, sorry. There we go. So simple in order, and this took, when it ran, 0.0 or 18 milliseconds is how long this took to run. So hopefully our out of order is going to run faster than 18 milliseconds. Otherwise, there's something very wrong with gem5. I'll be very embarrassed if I get this wrong too. I'll also say while we're waiting here, there it goes. So now it's finished. So we can open up the stats.txt. So that's the out of order stats.txt, and here's the in order stats.txt. Put them side by side. So in order took 18 milliseconds, out of order took 7 milliseconds. Great. So the out of order is a little bit more than twice as fast as the in order. And similarly, we can look at the IPC. The out of order's IPC is 1.47. The in order's IPC is 0.57. So we're getting a higher IPC as well. And you can look at other things too. You know, the cycles obviously are the same difference as the time, since they're running at the same frequency. And you could also look to see the number of committed instructions here, compare this to the committed instructions. Sorry. We compare these two committed instructions between the out of order on the left and the in order on the right. We see it's almost exactly the same of the number of instructions. Okay. So, any questions on that example?
Any questions on the example or about stats or anything? No questions.
Okay, great. So now that we've seen a little bit about how to configure a system using the standard library and then extend the standard library to model our own kinds of things, let's talk about controlling the simulation. So we're going to talk about how we control the simulation, improve performance, mark regions of interest, some fast forwarding, and some other stuff. Okay, so gem5, if you haven't realized, it took over 2 minutes to run that really simple thing that only took 7 milliseconds. Gem5 is very slow. This is only partially our fault. I'll say it's a little bit our fault. But we're simulating a lot. We're getting a lot of detail out of the system, and so it's going to be slow. Simulating a second in gem5 with a multi-core CPU takes about 24 hours on your host. So we're on the order of 100,000x slower than real life, which, to be honest, is not bad for a cycle-accurate simulator, but it's really slow. You can't run really big workloads, things that take minutes or hours in gem5. You'd be waiting for days or years. And essentially, there's a trade-off here between the amount of simulation time and your simulation fidelity. So Matt mentioned this too, that was in Lieben's book about how we trade off fidelity for accuracy. But the key idea here is when we're simulating with gem5, not everything in your workload needs to be simulated with very high accuracy. There are some things that we can simulate or even just emulate. And then whatever region of the application we really care about, we can simulate that at high fidelity. So you can always make simulations faster by simulating less. So for instance, this XKCD about random numbers. So a lot of simulations look something like this, especially when we're doing full system simulation. So we boot the kernel, we boot the rest of the operating system, like system D and things like that. We then start running the benchmark, but the benchmark has to load a bunch of data and initialize things. And then we get to the region of interest that we actually care about. So ROI stands for region of interest. So we execute the region of interest. This is what we want to actually look at. And then we finish the workload and clean up, which we also don't really care about. So we're going to talk about some techniques to really just focus on this ROI. So some techniques that we have in gem5. So one is to use syscall emulation mode or SE mode. And we'll talk about the trade-off between that and full system in a moment. We can use these different CPU models. So we've already seen that the O3 CPU takes a lot longer, but gives us a more accurate result compared to the simple in-order CPU. We can use checkpointing. So we can get to the region of interest that we care about, save a checkpoint, and then reload that and use that many times. We'll see some examples of that. We can also use KVM, which allows us to fast forward using the native hardware. We'll talk about that next. And then we can also do sampling. So if our region of interest is too big to simulate, we can even simulate a sub part of that region of interest. And Alan will be talking about in 30 minutes how to do that with alphys in gem5. Okay, so SE mode versus FS mode. So on the left-hand side, we have full system simulation. So in this case, everything is running in gem5. So the operating system is the Linux kernel. We're executing instruction by instruction of the Linux kernel in the simulated system. So this is also similar to, say, QEMU, where all of the guest is running, where you have a whole guest running inside the emulation environment. This is opposed to SE mode or syscall emulation mode. And SE mode is what we were using in the last couple of examples. In this case, what we do is we only really simulate the application and the hardware, and we let the host operating system simulate the operating system. So anytime the application does a system call, gem5 emulates that system call. So it does not gem5, the simulator does not execute the kernel code. The host executes the kernel code using the host's kernel. So this can speed things up a lot. We don't have to wait for things to boot. We don't, like, if you're doing file IO, we don't have to actually do the cycle level IDE controller and stuff. So especially for getting started with your system, testing things out, testing workloads, SE mode can be much faster. Let me pause here for a second. Any questions on SE mode versus FS mode?
Yes, we have a question.
Wonderful.
When you say speed up a lot, how much is a lot in general? Like what factor between?
So it really depends on what your application is. And being able to use SE mode for research also really depends on your application. So for instance, that IS application that we were just running, if we had done Linux boot beforehand with a timing CPU, it would have taken a couple of hours to boot Linux before we could run our application. So clearly it's much, much faster. If your application is really long and is mostly user mode, then the time is about the same. The other trade-off here is that if your application does interact with the operating system, does system calls, or if you're doing a multi-threaded environment where doing like few text system calls is important or OpenMP stuff is important, then you almost have to use FS mode because there's just no way that we can emulate those things in syscall emulation.
You have a question?
Is it possible to start executing in syscall emulation until the region with the interest and then change to full system simulation?
That's a good question. No, there's no way to do that, but we will see some examples of how we can fast forward things in full system simulation to almost get the same performance as syscall emulation mode. We'll see in a minute, but I'm going to say, spoiler alert, you should always use FS mode if you can. Personally, I only use syscall emulation mode for testing things. Then again, Alan is going to show you these alphys which is another example of how we can use Cisco emulation mode to get good fidelity. Any other questions?
So, okay.
Okay, great. Okay, so if we're doing full system simulation and we really just want to run the ROI, we have two different methods to do this in Gem5. So we can either fast forward to the ROI, and we're going to show the KVM CPU to do that, or we can take a checkpoint at the beginning of the ROI and then reload that checkpoint. So let's talk about KVM fast forwarding. So KVM is the kernel-based virtual machine. So this is a module that is in the Linux kernel. The way it works is it uses hardware virtualization extensions. So things like nested page tables, VM exit. I think that, so Intel calls this VMX, AMD calls it something else. What does AMD call it, Matt?
SVM, secure virtual machine.
SVM. So it uses these hardware extensions from Intel, AMD. ARM also has extensions for hypervisors that can use KVM, and RISC-V is coming out with them soon. And what Gem5 does is use these hardware extensions on the host as its CPU model. So in other words, the code that Gem5 is emulating is actually executing on the host CPU. So this is super fast. We can run essentially at native speed, but it comes with two caveats. One is your host must match the guest. And the other is that you get no timing information out of it. It's really can only be used for fast forwarding. Any quick questions here? We'll see an example of using KVM in a minute.
KVM questions? We got one.
It's not like a level upgrade, no.
The question is if it's cycle level accurate.
No, it is not. Like you don't get no information about it. It's only functional. So it functionally executes all the instructions, but you get zero timing information out of it. Yeah. But it's super fast, so you can use it for fast forwarding. Okay. Cool. So checkpointing is another technique we can use, which I'm running out of time, so we might not be able to see an example of this. But essentially the idea with checkpointing is you get up to a point in your application and running in Gem5, and then you can save all the architectural state of the system. And in fact, you can even save some of the microarchitectural state as well. Being able to checkpoint really depends on the models you're using in the simulation. So each model in Gem5 has to support checkpointing or not. But the really great thing about checkpointing is you can take that checkpoint once and then reload from that checkpoint many, many times. And when you reload from the checkpoint, you can even change some of the things about the system. You can't change everything. In fact, you can't even change that many things, but you can change a few. So there's these trade-offs between KVM and checkpointing. So KVM is really fast. It's really flexible because you can change your simulation system as much as you want every time you use KVM to fast forward. And it's flexible to software changes. So if you're using a new kernel, using a new runtime, even changing your application, you can do this really quickly with KVM. But the downsides of KVM are that it's non-deterministic. So we lose all the determinism in our simulator when we use KVM. The host must match the guest. So if you want to run an ARM system, you have to be on an ARM host. There's no RISC-V support yet in Gem5 for this. And KVM can really only fast forward the CPU. So maybe we have some ideas on how to do some other kinds of fast forwarding for GPUs and other things. On the other hand, we have checkpointing, which is cool because you can create the checkpoint once and run it many times. So if you're doing a big design space exploration, you can often use checkpointing to save a lot of time. And almost all devices and components are supported in checkpointing, whereas KVM, there's a lot of devices and components that are not supported. But with checkpointing, you can't change the software at all, really. It's whatever the checkpoint was taken with, that's the software that you're running. You can only change a few things about the simulated system. So you can change some parameters of your sim objects, but you can't change the objects themselves. And another downside is if you take lots and lots of checkpoints, you end up using significant disk space. Each checkpoint can be, hundreds of megabytes to many gigabytes, depending on how much memory you have in the system. Questions?
Questions about checkpointing?
So checkpointing is running like through Gen5 full simulation mode until the point and then just freeze it.
Yep, that's right.
Oh, Jason, you can hear them in the room. I don't have to walk around.
I did hear that. I cannot
Okay.
always hear them.
Gotcha, okay. Yeah, I just wanted to add, we will show checkpointing this afternoon, on the GPU side, so I think Jason mentioned there's not time, but we will show it later.
Okay, yeah, I might skip over my checkpointing example then. Cool. Okay, so one of the other things you might be asking is, how do we know where the region of interest is? So to designate the region of interest, gem5 has what we call magic instructions, or I'm trying to change the name of this to bridge calls, but we'll see if that catches on. But basically what this is a mechanism for the guest application, the thing running in gem5, to communicate with the simulator. So this is, if you're familiar with how virtualization works, this is similar to hypercalls, where the guest operating system is talking to the host operating system. So these are often called M5 ops. So this is another legacy term that's been around since M5. I'm trying to rename these things, but it's going to be a long process. So over on the right-hand side is an example. So we've been looking at this application IS. So if you look in the gem5 resources directory where we have the NAS parallel benchmarks, you can actually find this code where, if we're using these gem5 hooks, then we call this ROI begin function. We run the application, which in this case is quite simple, and then we call ROI end at the end of it. So inside this function, ROI begin, we have this special call to a function called M5 work begin, which can be implemented a number of different ways. But essentially, when the M5 work begin function executes in the gem5 simulator, it will call a function in gem5. So when the simulator executes this instruction, it calls a special function in the simulator that we can do cool things. And in fact, what happens is we essentially exit the simulation loop and can deal with this from Python and decide what to do. So I know this is a little bit confusing. I'm happy to take any questions.
Questions about regions of interest?
They always like that, with the books.
So yeah, I think I heard the question was like, is it always like this with the hooks? So gem5's interface is just this thing at the bottom, the M5 work begin. And then a lot of all the stuff in gem5 resources, we try to expose, or we try to make sure that all the resources have these ROI begin and end statements in them. To be honest, we're not very consistent with the way we do it, but somewhere or another, these functions get called. So it doesn't have to be if-def hooks.
Yeah, I think another reason those are there is you can run the application on hardware, so it's not going to try and run the Gen5 only instructions.
Yeah, that's exactly right. Okay, cool. So let's explore this in the next example. And then I think after this example, I'll probably turn it over to Alan, and then we'll, after lunch, finish up the standard library stuff. Okay, so let's go to the 05FS NPB. So the first thing we're going to do is we're going to change the obtain resource, and we're going to do x86 Ubuntu 2404 boot with systemd this time. So let's do that. Let me close everything and pull up the next example. Okay, so actually we're doing 04 KVM. Apologies. Okay, so in this file, we have set up the simulation. So we are going to use this messy 2-level cache hierarchy. So this means we're going to need to execute this with gem5 messy. Single channel DDR4 memory. We're gonna use the switchable processor, which we'll see in a minute. In order to get KVM to work in code spaces, we have to say use perf counters false. Usually you don't have to do this on your native system, but running on a virtual machine, we do. We're going to use this x86 board with our processor, memory, and cache hierarchy. And we're going to use 2404 boot, set the workload, and then we're going to append this kernel argument to where we want to boot up Linux and then be interactive. So this is an option here. And then we're going to create the simulator with one little extra thing, which is when we get an exit event, we want to call on exit. So let's talk about what we want to do here. So let me talk about this for a minute. So booting Linux is pretty complicated. There's a bunch of steps here. So over on the left, we have these steps. So first we boot the kernel, and we can add some command line parameters to the kernel when we boot it. Then we start systemd. So systemd is Ubuntu and most of the Linux flavors, the way that they start all the initialization processes and all of the daemons and everything that run in the background. Then after systemd boots, then we auto log in as the gem5 user. And when we auto log in as the gem5 user, we can optionally execute a script that is provided by the gem5 simulator. And in all of these disk images that are on gem5 resources, at least we're working to make this consistent across all of them, there's going to be, after we boot the kernel, a simulator exit event. Then after we log in as the gem5 user, there's another simulator exit event. Then after we execute our script, there's another simulator exit event. So that way you can kind of catch these exit events and make choices as to what to do during the boot. And then there's also options where we can either, skip doing systemd if maybe we don't care about all the background daemons running. And we can also skip doing executing a script. And so that's what we're going to do in this example, is skip this executing a script so we can get to an interactive terminal. So controlling the simulation events. So what we're going to do is update this onExit function in the KVM script. And we are going to, the first time we see an exit event, we're going to print exiting the simulation for kernel boot, because the first exit event is going to happen after kernel boot. Then we're going to yield false. So this onExit is a Python generator. And by yielding false, we're going to say, don't stop the simulation, keep going. Then the next exit event that happens, we're going to print exiting the simulation for systemd complete. And then we're going to also continue the simulation by yielding false. Then after that, if there's another exit, we don't have anything left in our generator, so it will just exit the simulation if there's another exit. So let's look at that example. So we're going to print exiting for kernel boot, yield false, exiting after systemd, yield false. Okay, so after making this change, we can run this script. So we're going to run gem5. We have to use gem5 messy in this case. Then we're going to run our 04 KVM. And that's it. Actually, yeah. So we can run this, and it will start running. So it's going to run, it's going to print exiting kernel boot, it's going to print exiting after systemd, and then it's just going to kind of hang there. So one thing we might want to do is actually connect to the simulated system and see what's going on. So while that's doing it, so we see exiting for kernel boot. So I'm going to create a new window here. And now let's go to gem5 utils, util term. So in this directory, so we now got our exiting after systemd. So in this directory, there's a couple of files. So this is in gem5 util term. So there's a term.c and a make file. So if we run make, we get this application called m5 term. So this is going to allow us to connect to the simulated system. This is basically just a specialized telnet connection. So we're going to run M5 term, and then the port, if you noticed it popped up and said, do you want to forward port 3456? I ignored that. And so 3456 is the port in which we can connect to the serial interface in gem5. We're going to run this. And what you'll see is that systemd finished. We had an auto login here. And it says interactive mode enabled, dropping to shell. And so now we have the gem5 shell. So I am now running inside gem5. So we can look at things, we have programs installed like GCC, and you can run benchmarks, whatever you want to do. This is running in KVM mode, so it's really fast. Let's see if there's anything else I wanted to say about that. Give me 1 second. Okay, I think that's all I want to say about it. Any questions about booting up in KVM?
Question about that or interactivity or exit events? It's like no questions.
Okay, so in our terminal, there's a program called gem5 bridge installed. Yes, gem5 bridge. And if we run exit, gem5 bridge exit, this will create an exit event in gem5. So we can do that. And you'll notice over here, gem5 printed user specified generator function list for the exit event exit has ended using the default, which is to exit. And so we exited the simulation. So you kind of see how we're actually inside the simulated system, we're able to communicate to the simulator. Okay, so there's lots of different kinds of exit events. We kind of use M5 exit for everything right now, but that's going to be, in the next version of gem5, this is going to be fixed. But there's lots of other exit events as well. The work begin and work end are probably the most common, which is what happens if you call M5 work begin or M5 work end. But there's lots of other exit events as well, which you can find in the simulator module in the standard library. So we talked about the M5 term. In order to connect to it, the default port is 3456, or if you have a bunch of gem5s running, you can increment that 3457, 3458, etc. Okay, so real quick, before we switch over to Alan, I want to talk about doing something with the ROI. So we're going to use this full system version of IS instead of the syscall emulation version. So what does this resource do when I say obtain resource? So if we go to this website, this link for the resource, this is the wrong link. Oops. Let me go to the right link real fast. We'll go through gem5 resources here in a minute. Okay, this is the one that I was looking for. So this is a workload, and what this is going to do is set up everything for us automatically. So it's going to get this kernel version. It's going to get this disk image. It's going to set a bunch of kernel parameters, and it's also going to execute this script after gem5 boots. So let's see what happens when we change this workload to use this full system IS. So I think we can go to FS, the next one, 05 FS NPB, and this should be all the same, except that we don't have this workload set. So we're going to obtain resource, this x86 Ubuntu 24 NPB ISS. Now we have the same on exit script as well. Okay, so now if we run 05, FSNPB, and I'm going to get over here this terminal, the M5 term ready to go. So I know I'm going kind of fast. Let me pause here for a second before I continue to see if people need me to go back to anything.
Is everyone able to follow along?
Okay, cool. So let's run this. And then as soon as this thing pops up to say port 3456 available, I'm gonna run M5 term. It's doing some loading the disk image in, reading it off disk, etc. And just so I know time zone wise, we're at noon, right?
Sorry, did you ask a question?
Yeah, we're at noon your time.
It's noon here, but there's 30 more minutes for
Perfect. Okay.
Alfie's.
Yeah.
For Al.
So I don't know if you could see that over Zoom, but the over here in the M5 term, it went through all of the loading of system D. Then it auto logged in with gem5. It executed this after boot script, which executed the NAS parallel benchmark IS, and it ran through IS. And so that ran to completion. So I want to just really quickly go through this before I turn it over to Alan. So this just ran it, and it didn't do anything on work begin and work end. So what we would like to do is some more interesting stuff on work begin and work end. So I want to define two more generators on work begin. And in this generator, what I want to do is print to the screen at work begin, and then do M5 stats. I want to reset my stats, and I also want to switch processors. So if you remember, our processor up here is a switchable processor, which has a KVM type and a timing type. So we're going to switch from KVM to timing using this function processor.switch. And then here we're going to yield false because we want to continue simulating. So I also want to define an on work end function or generator. And in this case, I want to print work end. And then I'm going to yield true in this case, because once we get to the end of the ROI, we really don't care about simulating anything else. We're done. So now let me set these up on the board. So exit event dot work begin. I want to run on work begin. And exit event dot work end. I want to run on work end. Okay. So with that, I'm going to rerun it. I will watch it with M5 term for fun as soon as it loads. So this time it should take a little bit longer to simulate since we're switching to a timing CPU. So we're booting gem5, booting system D, or booting the kernel, then booting system D. I imagine we're about to log in. We logged in, started this, and then it printed over here at work begin switching CPUs. So now this is going much slower over on the M5 term because we're actually simulating it in timing mode. So this will take about 30 seconds, not too much longer, probably almost exactly the same amount of time as it took in SE mode to run this. And then we'll actually be able to get the detailed timing statistics. So we got ROI end, and then printed work end, and we exited. So I know I went through that really fast. So we can look at the stats.txt if we're interested. And hopefully this took about the same amount of time as what it did in SE mode. So it took 16 milliseconds instead of, I think it was like 18 milliseconds in SE mode. So it's a little bit faster in full system mode because we're only doing the region of interest. We're not doing the initialization or the checking. So questions?
Any questions? No questions? Okay, then should we switch over to Alan now for the healthies part?
Yeah, so let me just say one last thing here. So yeah, the takeaway here is, you know, you can set up your system in Gem5 and then control it with the simulator module. And the simulator module allows you to do things like switching CPUs, taking checkpoints. And in Python, you get to decide what to do to control the simulator. You're not tied to any one person's idea of what to do. You can choose what points in the application to do what with the simulated system. Okay, so that's all I wanted to say there. So we're not going to do checkpointing now and restoring, but when we get back after lunch, I'll do Gem5 resources. So yeah, I'll turn it over to Alan now.